All right, welcome back, and we are going to be looking at section 6.1 today. So what we're going to be looking at are exponential growth and decay functions. We want to be able to use these exponential models to solve real-life problems. But before we can do that, we have to understand what an exponential function is. An exponential function has this form: y equals a, b to the x, where a cannot be 0 and the base b has to be a positive real number other than 1. So let's take a look at a function that would meet those requirements. So I have to put in some number for a. It can't be 0, so how about if I just use 2? I have to use some number for b, and I'm going to have to put times here just so that it doesn't have those numbers right side by side. This will be better. So I want a base b that's a positive real number other than 1. So how about if I just use 1.2? And then I'm going to raise that to the x power. All right, so the way the calculator would compute this is it has to follow order of operations. So it's going to take this number, raise it to the x power. If we don't want to use a number so complicated like 1.2, let's just change it to 3. We'll make it an easier number to start with. So the calculator is going to do 3 to the first, then times 2, 3 to the 0, then times 2, 3 to the negative 1, then times 2. So that's how it's going to get its table of values. So if I graph this now, here's the way it's going to look. Just like that. That is a growth function, and here's the reason why. The a value that I chose was 2, and that's greater than 0. The b value that I chose is greater than 1, so therefore that's a growth function. As x gets higher and higher and higher, as x gets greater, y gets greater. All right, now let's look at a decay function. So to have a decay function, a still needs to be something greater than 0, it is, but now my b value has to be something in between 0 and 1. So how about if I just make it 1/3? Okay, so now I've got that. I'm going to graph that. So now I've got my a value was 2, my b value was 1/3, and here's the way a decay function looks. So in a decay function, as my x gets larger, my y value gets smaller and smaller and smaller. So that when I have this factor right here, this b value in these functions that I put up here, those are called my exponential growth and decay factors. So in the first one, my growth factor is what the first one would be called because it was a growth function. That b value was 3. So we had the growth factor of 3 in the first one. In the second one, this is the decay function, and my decay factor was 1/3. Okay? Now, if I rewrite it so that it's in this form, this y equals a plus or minus r to the t, this r value is now going to be called either a growth rate or a decay rate. Let me show you that real quick with this one. I could rewrite this problem as y equals 2 times 1 minus 2/3 to the x. Can you see how that would be equivalent? 2 is the same. 1 minus 2/3 is the same thing as 1/3 to the x. So in this problem, if I asked you for the decay rate instead of the decay factor, the decay rate here would be 2/3. Okay, and we're going to get into that as we go along. The asymptote is the line that the graph approaches more and more closely. So looking at this function again, this decay function, this is approaching 0. If I hit trace and I hold this key down, you're going to see that this y value, it just keeps getting closer and closer to 0. It's never going to go lower than 0. You might be thinking, what are these numbers? Well, this is 1.99 times 10 to the negative 6. So that's 0.0000199, etc. So when we have these asymptotes, it's going to be a horizontal asymptote for these exponential functions of y equals 0. All right, so looking at more basic functions now. If I have just f of x equals b to the x and b is greater than 1, That's going to be an exponential growth function with a base of b. This shows us that general shape. So we can see that the x-axis is going to be the asymptote. The equation of that x-asymptote is y equals 0. And we can see that the graph is going to rise from left to right. It always passes through these points of 0, 1, and 1b, b meaning the base. These are going to be called our key points. Our key points are always going to be 0, 1, 1 base. Here's why. If I plug 0 in here, no matter what this base is, any number raised to the 0 power is 1. Any number raised to the first power is just going to be the number itself. This also tells us that the domain of this exponential function is all real numbers, and the range is going to be y greater than 0. It will never be equal to it, greater than 0. Graph each of the following. Make a chart to help. State the growth and decay factor, the domain, the range, and the equation of the asymptote. Make a chart. So my chart, I'm going to have x and f of x. If we plug in 0 for x, what is 2 to the 0? Anything to the 0 power is 1. Plug in 1. What is 2 to the first? Well, that's 2. I could keep going with this, but it's really not necessary. When I ask for the key points, I'm talking about those 2 points. So the next thing they ask us to state is the growth or decay factor. We have a growth factor of 2. The domain, I'm going to do my little sketch as I go. I have the point 0, 1, and I have the point 1, 2. I know these exponential functions never cross this x-axis. So here's the way it's going to look. So I've got my growth factor. Second thing, the domain, that's negative infinity to infinity. The range, that's going to be from 0 to infinity. And then the equation of the asymptote, that's going to be the x-axis, which is y equals 0. All right, let's do this problem now. We're going to make our table of values. We plug in 0 for x. Anything to the 0 power is 1. We plug in 1 for x. 1/2 to the first power is 1/2. Those are our key points. I could keep going if I wanted to, but that is enough information to graph. So I've got 0, 1, and I've got 1, 1/2. And then I know it's never going to go below that x-axis. And so that's the way it's going to look. So in this case, I have a decay factor of b, and b was 1/2. I have my domain is negative infinity to infinity. That range is going to be 0 to infinity. Range is those y values. It keeps getting closer and closer to 0. And then that asymptote is y equals 0. And these would be the key points if we were asked for them. All right. So here's something more about decay functions. This is just saying that if we have the space between 0 and 1, in other words, that decay factor is in between 0 and 1, then we're going to have this type of graph, which we just did a minute ago. The graph is always going to fall from left to right, and it's always going to pass through these key points of 0, 1, and 1b. And again, the x-axis is going to be the asymptote. We already talked about that. All right, so now we're going to graph this right here. State whether the function represents exponential growth or decay. Graph. State the domain of the domain, the range, and the equation of the asymptote. This might be a good place for you to pause the video and try this on your own, or you can just watch. All right, so I'm going to make my table of values. If I plug in 0 for x, anything in the 0 power is 1. Plug in 1, I get 0.75. I'm going to go ahead and graph. I've got 0, 1, and I've got 1.75. So I can see that this is going to be decay. This is going to be a decay function. The domain is going to be negative infinity to infinity. What's the range going to be? Yep, 0 to infinity. and then that asymptote again, it's going to get closer and closer. That's y equals 0. All right. Now, another way we can write exponential growth and decay models is in this form right here. I mentioned that up above, but I didn't talk about it a lot. But if we have exponential growth, we can write it like this. If we have exponential decay, we can write it like this. Rewrite the functions in this form, either this one or this one. Then state the growth or decay rate. All right, well, what I want to do is A is not going to change, but this number, I want to write it as 1 plus or 1 minus. To keep it equivalent to 4, it would be 1 plus 3 to the t power. So now we know that since this number here is greater than 1, then I know then that I'm going to have a growth rate of 3. Okay? Now, if they had asked for that as a percent, we could say it's 300%. All right, let's look at the next one. So this one, I want to rewrite it. So it's y equals a. 0.25 can be rewritten as 1 minus 0.75. That's equivalent right there to 0.25. So because we're subtracting, anytime we add, we know it's going to be growth. And anytime we decay, or subtract rather, that R value, we know it's going to be decay. And so in this case, the decay rate is 0.75. That can also be written as 75%. You'll have to see which way they want you to write it when you do your big ideas assignment. All right, now, these problems are a little bit tougher. Notice that in these formulas, we have to just have a t here. We can't have anything else. So what I'm going to have to do is I'm going to have to rewrite this one as a and then 3 to the 1/2 times t. Isn't that equivalent to t over 2, 1/2 times t? So to get this into the correct form, I'm going to have to do y equals a 3 to the 1/2 times t. That's still equivalent. So now I need to know, what is that? What is 3 to the 1/2? So I'm going to do 3 raised to the 1/2, and I get this number. Okay, we'll round to the nearest 3 decimal places. So this is going to be y equals a. Another name for 3 to the 1/2 is 1.732 to the t. Well, I can now see that this is going to have to be growth. I want to rewrite it as y equals a times 1 plus 0.732 to the t. And so the growth rate on this one is 0.732 or 73.2%. All right, why don't you pause the video, try this one on your own. All right, so on this one, I would have to say it's y equals a, and then I have 0.5. I can't write it like that, so I have to think of it as 1/9 times t. So it's going to be 0.5 to the 1/9 to the t power. So I have to actually figure this out. And that's going to be another name for this is a, and then another name for all of that is 0.926, rounding to the nearest 3 decimal places. I don't know if they'll have you go to the hundreds or 3 decimal places in big ideas, but just read it carefully. So now I'm going to have y equals a. Another name for this would be 1 minus, let's see, what is 1 minus this? So it's going to be 1 minus 0.074 to the t. That's another name for this number. If I wanted to check, I could do 1 minus 0.074. It should be equivalent, and it is. All right, so now I know I'm going to have a decay rate of 0.074 or 7.4%. All right, last thing here, these are the real world applications. So compound interest. If we consider an initial principal, P, principal is the amount of money that we put into an account, and we're going to deposit it into an account that pays interest at an annual rate, R, and that's always going to have to be expressed as a decimal, compounded in times per year. The amount A in the account after T years is going to be given by this formula. All right, so here's the formula. This is going to be our end amount in the account. This P is our initial amount that we put in. This is our interest rate as a decimal. This is the number of times it's compounded, number of times compounded, and that's the number of years. Okay, if you need to, you can go back and read through it. How much money could you put in the savings account? So we're going to think, like right now, how much money could you put into a savings account? Maybe you've got $500. Let's say $500. All right, so we're going to put that $500 in, and we want to know how much money are we going to have after 4 years with this interest rate. So let's see what happens. We want to know what's the end amount. We're saying 500 is our beginning amount. 1 plus our interest rate is 2.75. Well, that would be written as 0.0275. To change a percent into a decimal, you drop the percent and move 2 places to the left. And then divided by the number of compoundings per year. Well, if it's compounded monthly, that's going to be 12 times per year. Up here, we have the number of compoundings per year, which is 12, times the number of years, which is 4. So we can type this in. And then I just like to go ahead and multiply that, 48. And here's how much money you would have after 4 years. So if you start with $500, after 4 years at that interest rate, you're going to have $558.07. And guys, that's the way I expect you to write money. It's always rounded to the nearest cent, okay? And it should have a dollar sign, decimal, etc. Now, that's not bad, right? You're going to make $58. But $58 over 4 years is not that great, right? So what if I took that same problem and I'm going to make it, say, $50,000? What do you think is going to happen? Well, let's see if you're right. So if I make this 100 times as large, do you think that this will be 100 times as large? All right, well, let's see if you're right. It is, isn't it? So if the amount of money I put in is 100 times as much, then the amount of money I'm going to have at the end is also going to be 100 times as much as it was back here. So now if I put in $50,000 with that same interest rate, I would have made $55,806.88. All right. Use the given information to find the amount A in the account earning compound interest after 5 years when the principal is $12.50. And now we're going to use an interest rate of 2.25% compounded quarterly. All right. So how much money are we going to have at the end? Our principal is $12.50. Using our formula, it's going to be 1 plus our interest rate. Think of how you write that as a decimal, 0.0225 over, now if it's compounded quarterly, that means 4 times a year. And so 4 is going to go there. How many years? 5 years. So we're going to raise it to the number of compoundings of 4 times 5. All right, let's type it in. And we should get $1,398.40. We're always rounding to the nearest cent. Okay? All right, last problem here. The number of bacteria, Y, in thousands in a culture can be approximated by the model Y equals 100 times 1.99 to the T, where T is the number of hours the culture is incubated. Tell whether the model represents exponential growth or exponential decay. All you have to look at right there, what's it going to be? You're right, growth. Identify the hourly percent of increase or decrease in the number of bacteria. Well, to do that, I'm going to have to rewrite that in that other form. So this is going to be y equals 100 times 1 plus 0.99 to the t. Now I've got it in that form where I can see that growth rate. And that's also going to give me the hourly percent of increase. So that's going to be 99%. That's going to be the hourly percent of increase. Estimate when the number of bacteria will be 1 million. Okay, so we want to know when are we going to have 1 million. Okay, so this is in thousands. Y is always in thousands. So if I have 1 million, if it's in thousands for the formula, I shouldn't really make this 1 million. I should make it, I'm going to divide it by 1,000 to figure out how many thousands I've got. And so I've got 1,000 thousands, so I'm going to have 1,000 is what I want to have equals 100 times 1.99 to the t. This is a coefficient. I'm always allowed to divide by this number. I am not allowed to divide by this number. Another thing, if I were plugging in for t, I would do this raised to the t, then times 100. So we can never multiply these two. I am, though, allowed to divide by 100. So this is now going to become 10. Now, this is not something I can solve. I mean, I could estimate it. Think about it. I know 2 to the first is 2. I know 2 to the second is 4. I know 2 to the third is 8. And I know 2 to the fourth is 16. This answer for t has to be in between 3 and 4. But when I come across a problem like this that I can't solve, instead of just estimating or guessing, think about what I can do. I can always solve an equation by going to y equals. I'm going to put 10 in for y sub 1. I'm going to put 1.99 raised to the x in for y sub 2. I want to know where are these equal. So I'm going to do a zoom 6. Oops, y equals 10's up there kind of far. I'm going to extend my window just a little bit. In the y direction, I want to be able to see that clearly, so I'm going to make it 20. And here we go. So now I want to find out where is it that they're equal to each other. So second trace, calculate a value, find that point of intersection, enter, 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 and then 3.346. At 3.346 hours, that's when we will have 1 million bacteria in there. Okay? All right. So, guys, when you're watching these video notes, what you should do is sometimes pause the problem. Watch an example, pause it, try it, and then, you can just fast forward, go on to the next problem. Try these on your own. You've got to be an active learner. You don't just sit and get. You got to be active take an active part in your learning. All right.